How do stars come into being, live, and die? We briefly touched on the topic of star formation in a recent video about the mystery of how stars were born in the early universe. And in the comments under that video, many of you, my dear viewers, expressed interest in a more detailed video about how the processes of star formation and stellar evolution take place. All stars in the universe form as a result of one and the same process: the gravitational collapse of clouds of interstellar gas, consisting mainly of molecules of hydrogen and atoms of helium, as well as a small amount of other elements, including microscopic solid particles known as cosmic dust. Under the influence of their own gravity, the matter in these clouds effectively falls toward the center of mass of the gas cloud. The gas density in its center begins to increase rapidly. This process is called gravitational collapse. As the gas is compressed, its temperature also rises, and the simultaneous increase in density and temperature would normally lead to an increase in pressure that would oppose gravity. However, when heated, all substances begin to emit electromagnetic radiation, the very radiation that allows us to see objects in a thermal imager or to see the glow of heated metal with the naked eye. This radiation, produced by the molecules of the gas cloud and by the tiny solid dust grains within it, efficiently cools the cloud by carrying away thermal energy. Therefore, in reality, no significant heating occurs. The collapse of the cloud proceeds at a constant temperature, or, as physicists say, in an isothermal regime. Pressure still increases because the density of the gas rises, but the increase in density also strengthens gravity. As the cloud contracts, gravity grows even faster. Thus, the gas cloud compresses at an ever-increasing rate. Yet as the gas density in the center of the cloud grows, the concentration of dust within that gas also rises, and the dust begins to absorb molecular radiation efficiently, trapping it inside the cloud. The thermal energy released during gravitational collapse and converted into electromagnetic radiation can no longer escape. The cooling system ceases to function, and further compression leads not only to an increase in density, but also to a rise in temperature. The pressure of the gas begins to increase faster than gravity, and at a certain stage, the two forces come into balance. The region in which the dust concentration, as a result of compression, becomes high enough for the medium to turn opaque to thermal radiation becomes stabilized. A stable clump of gas forms, whose density is high by cosmic standards, on the order of 10 to the power of -10 grams per cubic centimeter. This is roughly 10 million times lower than the density of atmospheric air, but roughly 10 billion times higher than the initial density of the gas cloud before the onset of collapse. In astrophysics, this gas bubble, formed in the center of the collapsing cloud, is called the first core. The process of its formation takes on the order of 100,000 years. After the formation of the first core, the compression process stops, but matter from the outer, less dense layers of the cloud continues to fall onto the gas bubble of the first core. Its kinetic energy, acquired during the fall, is transformed into thermal energy, causing the bubble to heat up. The process of releasing gravitational energy and converting it into heat is called accretion. The outer surface of the bubble can still cool through radiation, which means its temperature will always remain lower than the temperature deeper inside the bubble. For the first time, a temperature gradient appears within the matter of the future star. This process continues until the temperature at the center of the gas bubble reaches approximately 2000 kelvins. Once this temperature is reached, the kinetic energy of collisions between hydrogen molecules inside the bubble becomes sufficient for these molecules to begin dissociating, breaking apart into individual atoms. Energy is spent on molecular dissociation. That is, the gas begins to cool, which leads to a decrease in pressure. But in reality, something else happens. As cooling begins, gravity starts to dominate over pressure, and the gas bubble begins to contract again, rapidly and with an ever-increasing speed. This process continues until all hydrogen molecules in the bubble have dissociated and the future star loses its cooling mechanism. Now, a further decrease in volume will once again lead to an increase in temperature and pressure, meaning that compression will cease. At the location of the former center of the first core, a comparatively dense gas droplet forms, the so-called second core, whose density may reach hundredths of a gram per cubic centimeter. This is already tens of times higher than the density of air in the Earth's atmosphere. It is no longer a cloud, but a fairly dense and hot droplet that already resembles a star. Astrophysicists refer to such objects as Class 0 protostars. However, they cannot be seen with the naked eye. They are surrounded by a light-absorbing cocoon of gas and dust. Against the background of brighter cosmic structures, for example, emission or reflection nebulae, such cocoons appear as dark clumps, the so-called Bok globules. The maturation process consists mainly of the accretion of material from the gas and dust cocoon onto the surface of the protostar, which leads to an increase in the protostar's mass and temperature. The more massive the gas cloud is, the more matter the protostar can absorb during its maturation, and the hotter it will become. In this way, the foundation is laid for a fundamental pattern characteristic of all stars. The greater the mass of a star, the hotter it will be compared to other stars at the same stage of the stellar life cycle. The protostar also gradually contracts in size, increasing its density and once again heating up as it compresses. This happens thanks to an interesting mechanism known as the Kelvin-Helmholtz mechanism. The hot surface of the protostar emits electromagnetic radiation into the surrounding space, which causes it to cool. Cooling leads to a decrease in pressure and therefore to compression under the influence of gravity. The contracting outer layer of the star squeezes the underlying gas layers in the same way a rubber balloon's shell presses on the air inside it, increasing the air's density and therefore heating it further. This is a very important and somewhat counterintuitive point. By losing energy through one mechanism or another, the star contracts, and by contracting, it heats up. In other words, if we somehow cool a star, its temperature will not fall, as we might expect, but will rise. This property of stars as gravitationally bound thermodynamic systems is known as negative heat capacity. Thus, inside its cocoon, the protostar increases in mass, decreases in volume, and heats up thanks to accretion and the Kelvin-Helmholtz mechanism. As the protostar continues to heat up, its gas begins to ionize gradually. Just as earlier, upon reaching a certain temperature, gas molecules began breaking apart into atoms. Now, at higher temperatures, the atoms themselves are destroyed as they lose their electrons. The matter of the protostar undergoes a phase transition, turning from gas into plasma. The intensity of thermal radiation emitted by matter is proportional to the fourth power of its temperature. In other words, as the protostar heats up, it begins to shine brighter and brighter. At a certain stage, the radiation becomes so powerful that when we calculate the thermo- and hydrodynamics of the star, we must take into account not only the intrinsic pressure of the gas, or more precisely, the plasma within the star, but also the specific radiation pressure of the light it emits. Furthermore, the radiation of the star begins to exert a strong influence on the gas and dust envelope. The envelope heats up and begins to slowly blow away into the surrounding space. At the same time, more and more of this envelope is absorbed by the protostar. The gas and dust cocoon is gradually destroyed, and at a certain stage the protostar becomes visible in the optical range. A young star is born into the surrounding universe. Strictly speaking, it is not yet a full-fledged star, although in its external properties it already strongly resembles one. A sufficiently hot plasmasphere with surface temperatures of thousands of degrees and central regions reaching hundreds of thousands of degrees. However, to be considered a true star, such objects, also known as Tauri stars, still lack the most important feature. The temperature and density of the matter in their centers are still insufficient to initiate thermonuclear reactions. The key heating mechanism of a protostar, accretion, is now largely unavailable because the gas and dust cloud that previously served as their power source has already dissipated. Their primary mechanism of further heating is therefore the same Kelvin-Helmholtz mechanism, slow gravitational contraction caused by the cooling of the surface through radiation. This is a long process. While the entire formation of a protostar, from the onset of cloud collapse to the birth of a Tauri star, takes several 100,000 years, the maturation of a star until the ignition of thermonuclear reactions takes tens of times longer. During this process, the radius of the star will shrink by 2 to 3 times, and the temperature will rise by 1.5 to 2 times. Finally, the long-awaited moment arrives. The temperature in the core of the star reaches approximately 15 million kelvins, the threshold at which thermonuclear reactions begin, fusing helium from hydrogen. the star officially becomes a full-fledged star. However, not all Tauri stars are capable of growing up. The smallest among them, those whose mass is about 7.5% of the mass of the Sun or less, will never be able to ignite thermonuclear reactions in their interiors. Such stars are, in a sense, born prematurely. The gas cloud that formed them was too small, and during maturation, accretion of material onto the stellar surface did not have enough time to heat them sufficiently. Yes, after hatching from the egg, such stars continue to warm up through the Kelvin-Helmholtz mechanism, but the capabilities of this mechanism are limited. Matter cannot compress indefinitely. At a certain stage of compression, the plasma transitions into a state known as degenerate electron gas, which we discussed in more detail in our video about exotic states of matter, and it becomes impossible to compress it further. Once degeneracy is reached, compression, and therefore further heating, becomes impossible. And if by that moment the star has not heated to the temperatures required to ignite the fire of thermonuclear fusion, then it will never ignite. The protostar will never become a true star, transforming instead into what is known as a brown dwarf, a relatively dense but low mass and cool clump of plasma. I would like to draw attention to an important point. The stage of Tauri stars is the first at which different evolutionary scenarios for stars begin to appear. Up to this moment, all stars in the universe, without exception, evolve in essentially the same way. The specific values of parameters such as mass, density, and temperature may vary, but the overall sequence of processes remains the same. Here, however, we encounter the first branching point. A protostar will either become a real star or transform into a brown dwarf, gradually cooling as it radiates from its surface. But of course, we are more interested in those stars that do manage to ignite their thermonuclear furnaces. Let us look at what happens to them afterward. Before the onset of thermonuclear reactions, a star loses its stored energy through radiation from its surface, which leads to its contraction and heating. But now, within the star, its own internal energy source ignites, capable of compensating for these losses. If the thermonuclear furnace inside the star produces more energy than the star radiates from its surface, then the total energy of the star will increase. Conversely, if radiation carries away more energy than thermonuclear reactions produce, total energy of the star will gradually decrease. But earlier, we said that stars, as gravitationally bound thermodynamic systems, possess negative heat capacity. When their energy increases, they expand and cool, and when their energy decreases, they contract and heat up. And this is exactly what happens to a star that has just come of age. At first, temperatures high enough to initiate thermonuclear reactions are reached only in the very center of the star, within a very small region, and the amount of energy produced there is very small. The thermonuclear furnace cannot warm the still cooling star, and the star continues to contract, heating up more and more. The zone in which thermonuclear reactions occur expands, and the temperature at the center of this zone becomes significantly higher than the ignition temperature, which leads to an increase in the intensity of the reactions. The stellar nuclear furnace burns ever more strongly, and at a certain stage, energy production becomes equal to the energy lost through radiation. The star stabilizes and reaches a state of equilibrium. The more massive, larger, and hotter a star is, the more energy it radiates into surrounding space from its surface, and therefore, the more intensely its internal thermonuclear reactor must work. Thus, for the smallest true stars, it is enough to contract just a little after ignition to reach equilibrium. More massive stars, on the other hand, continue contracting for longer and contract and heat up far more strongly. This is why the lightest true stars, with masses from 7.5% to 47% of the solar mass, have surface temperatures from about 2,250 to 3,850 kelvins, whereas our Sun has a surface temperature of roughly 5,800 kelvins, and the most massive stars of spectral class O, whose masses begin from about 20 solar masses, are heated to 50,000 degrees and higher. Temperature affects not only how much energy a body radiates, but also the form in which that energy is emitted. The colder a body is, the more long wavelength components appear in its spectrum. As temperature increases, the spectrum contains more and more short wavelength components. The average wavelength of the emitted light decreases. This is why the lightest and coldest stars are called red dwarfs, while the hottest are called blue giants. These names are conventional. Red dwarfs actually have a reddish-orange color resembling ochre, and blue stars emit most of their energy in the violet and ultraviolet parts of the spectrum. The Sun is even more interesting. From the standpoint of spectral classification, it is a yellow star, but its visible color is white, and it emits most of its energy in the green part of the spectrum. The explanation is that we, having evolved under sunlight, perceive light of this particular spectral composition as white. As for why astronomers call the white sun yellow, that is connected to certain specifics of photometric methods used in stellar studies. We will not dive into those details now so as not to draw the narrative out. Just accept the fact, the names of stellar spectral classes do not always accurately describe their visible color. For example, the brightest star in Earth's night sky, Sirius, which appears bright blue to the eye, is classified by astrophysicists as a white star. After the thermonuclear reactions that fuse hydrogen into helium ignite, the star enters the longest period of its existence, the stage of life as a main sequence star. The term comes from the so-called Hertzsprung-Russell diagram, the primary tool for stellar classification in modern astronomy. On this diagram, the vertical axis represents stellar luminosity, and the horizontal axis represents color, essentially temperature. Stars that generate energy by converting hydrogen into helium form a beautiful curve on this diagram, which astrophysicists named the main sequence, even before they understood what exactly they were looking at. Thus, in main sequence stars, the production of energy in the thermonuclear furnace is balanced by the energy carried away from the surface through radiation. Main sequence stars are stable. Their energy, and therefore their volume, temperature, and other parameters, does not change as long as fuel, meaning hydrogen, remains in their thermonuclear core. Or rather, it would be more correct to say that these parameters change almost imperceptibly. In reality, as main sequence stars age, all of them, including our Sun, gradually heat up and increase in size. As we have mentioned, in the stellar core, which in the case of the Sun, occupies approximately 20% of its radius, the thermonuclear reaction converting hydrogen into helium takes place. From 4 hydrogen atoms, 1 helium atom is formed. Consequently, over time, the total number of particles in the stellar core decreases. But gas pressure, although in the case of the solar core this gas is extremely exotic, with a density several times higher than that of the densest metals, is directly proportional to the number of particles. Therefore, as hydrogen is converted into helium, the pressure in the core drops, and under the weight of the overlying stellar layers, the core begins to contract. And when it contracts, it heats up, which increases the intensity of thermonuclear reactions. The stellar furnace begins producing more energy, which disrupts the equilibrium. Usually, an increase in energy production causes a star to expand and cool, the same effect of negative heat capacity. But in this case, the effect does not work as expected. Yes, the star indeed attempts to radiate more energy from its surface, and to do so it must expand. But at the same time, the core continues to contract. Because of this contraction, the star cannot expand enough to radiate away all the excess energy, and as a result, it heats up. And the increase in temperature and surface area leads to an increase in total luminosity. Our Sun, for example, is currently increasing its luminosity by 1% every 100 million years. According to calculations, in roughly 1 billion years, the increasingly overheated Sun will bake the Earth so strongly that it will evaporate all water, making our planet uninhabitable. Thus, main sequence stars do indeed gradually increase in size and temperature. However, this process occurs extremely slowly, thousands of times more slowly than, for example, the Kelvin-Helmholtz contraction and heating occurring in Tauri stars. Therefore, on astrophysical timescales, main sequence stars can be considered approximately stable, and this will remain true as long as hydrogen continues to be available in their nuclear furnaces. How long will this continue? It depends on the size of the star, and the dependence is counterintuitive. At first glance, it seems that the larger the star, the longer its hydrogen supply should last. But in reality, it is exactly the opposite. The more massive the star, the faster it exhausts its fuel. To maintain energy equilibrium, large hot stars must burn far more hydrogen per unit time to compensate for the enormous energy lost from the huge area of their incandescent surfaces. Therefore, their thermonuclear furnaces are larger, their temperatures are higher, and hydrogen burns out significantly faster. Moreover, in the smallest stars, the entire volume of the star is involved in convection. Hot material from the incandescent center rises toward the surface, where it cools through radiation and is replaced by material from the cooler outer layers. The central regions of more massive stars, including our Sun, are compressed too strongly by gravity to sustain convection. There is no full exchange of material between the stellar core and the surface. Or more precisely, such exchange happens only in part of the volume. Thus, while red dwarfs can rely on all the hydrogen they possess, more massive stars can use only the hydrogen that was originally present in their cores. This is why the smallest red dwarfs have enough hydrogen to last hundreds of billions or even trillions of years. Stars like our Sun will remain on the main sequence for about 10 billion years, and the most massive blue giants of spectral class O will exhaust their fuel in tens or even single-digit millions of years. On cosmic timescales, such stars burn out almost instantly. What happens after a star exhausts its hydrogen reserves? Taking into account everything we have already learned about stellar physics, the answer is straightforward. Once deprived of its internal energy source, the star will cool by radiating from its surface, and therefore will contract and heat up. The Kelvin-Helmholtz mechanism will switch on again, just as it once heated and compressed Tauri protostars. The consequences of this process will also be similar. Light stars with masses less than roughly 1/2 of the Sun's mass will contract until their plasma transitions into a state of degenerate electron gas, just as happens in brown dwarfs. However, in this case, both the initial, pre-contraction, temperature of the star and its mass will be much higher. So by the time electron degeneracy begins, the star will have heated up far more, reaching impressive temperatures of tens of thousands of degrees, even at the surface. Electron gas has an interesting property. The higher its temperature, the greater the density it can reach before degeneracy sets in. Therefore, the hotter the star and the white dwarf that eventually forms from it, the more it can contract. This leads to a counterintuitive size-mass relationship for white dwarfs. The more massive the white dwarf, the smaller its size. The lightest white dwarfs have radii of about 4 Earth radii, whereas the most massive ones are only about 2 to 3 Moon radii. Stars with masses exceeding 1/2 of the Sun's mass do not transform into white dwarfs immediately. They face a more interesting fate. During Kelvin-Helmholtz contraction and heating, their cores will reach temperatures of roughly 150 million degrees, which is sufficient to ignite a thermonuclear reaction whose fuel is the helium accumulated in earlier stages. This helium fusion will produce predominantly carbon, as well as smaller amounts of oxygen, nitrogen, neon, magnesium, and fluorine. Having received a new source of energy, the star stops contracting and begins searching for a new equilibrium position at which it can radiate the energy it produces from its surface. Thermonuclear burning of helium releases approximately 10 to 12 times more energy per unit time than thermonuclear burning of carbon. In other words, during the helium burning stage, the star receives far more energy than it did while it resided on the main sequence. And in order to radiate this energy into the surrounding environment, it must acquire a surface area larger than it had during the hydrogen phase of its life cycle. Contraction is replaced by expansion, and by a substantial amount. For example, the Sun during the helium burning stage will increase its radius by roughly 10 times compared to its current state. When such expansion occurs, the surface temperature of the star decreases. For the Sun, this decreases by roughly 2,000 degrees, from 5,800 to 3,700 degrees, and therefore its color becomes redder. These swollen and reddened stars, which have switched from hydrogen to helium fuel, are therefore called red giants. The word red is once again conventional. It reflects not the actual color, but the reddening relative to the color the star had during its main sequence phase. Red giants formed from the most massive stars may appear optically yellow, white, or even blue. It is also very important to understand that the cores of red giants consist primarily of helium. In their outer envelopes, hydrogen usually dominates, hydrogen that did not participate in thermonuclear burning during the previous stage of the star's life. Since thermonuclear burning of helium proceeds more intensely than hydrogen burning, a red giant will exhaust its helium reserves considerably faster. If hydrogen lasts, for example, the sun roughly 10 billion years, then helium will last only about 1 billion years, after which the star will again enter a stage of contraction and heating due to the Kelvin-Helmholtz mechanism. Stars similar to our sun will, through this process, eventually turn into white dwarfs. Stars with masses of about 7 to 8 solar masses will, during contraction, be able to reach temperatures of 500 to 800 million degrees, which will allow them to begin using carbon as fuel with the formation of neon, sodium, magnesium, and other elements. Thanks to this, such a star will avoid turning into a white dwarf and will remain in the red giant stage somewhat longer. Stars with a mass of about 10 solar masses can then switch to neon burning, producing oxygen and magnesium. Stars of about 15 solar masses can proceed to oxygen burning, producing argon and silicon. And stars of about 20 solar masses can proceed to silicon burning, forming iron, nickel, and cobalt. This is the end of the chain of thermonuclear transformations. The fusion of iron nuclei no longer releases energy, and therefore, regardless of how massive a star is, it cannot use iron as fuel. These most massive stars, by the end of their lives, become a complex, layered sandwich consisting of multiple shells of different chemical composition. Hydrogen in the very outer layer, beneath it a layer of helium, then a layer of carbon, and deeper still layers of neon, oxygen, and silicon, with an iron-nickel core at the very center. Such stars are not destined to become white dwarfs. They face a far more dramatic fate. They will explode as supernovae. We have a separate video dedicated to this astonishing phenomenon, so we will not delve too deeply into its physics here. We will mention only the key points. During the Kelvin-Helmholtz compression of the stellar remnant with an iron core, the temperatures and pressures increase to such an extent that a process called electron capture begins in the core. Atomic nuclei absorb electrons, turning protons into neutrons and releasing neutrinos. Neutrinos possess enormous penetrating power, and even many kilometers of stellar plasma, compressed to monstrous densities, cannot stop them. As neutrinos escape from the stellar core, they carry energy away, thereby opening a new cooling channel, which greatly increases the rate of stellar contraction. In addition, the neutronization process leads to the near-complete disappearance of electrons, meaning that compression will no longer be halted by electron degeneracy. The core of the star will contract rapidly until the packing limit of neutrons is reached. The matter of the star transitions into a state of degenerate neutron gas, forming a compact and extremely dense core of neutron matter. The outer layers of the star under its gravity begin to fall into this newly formed abyss, and then, upon reaching the core, rebound from it. A shock wave forms, propagating outward from the center of the star and dispersing the incandescent stellar matter into surrounding space. At the center remains the dense, extremely hot, degenerate neutron core. These objects we call neutron stars, and we discussed them in detail in one of our earlier videos. For the most massive stars, with masses of about 25 solar masses and higher, the temperatures and pressures during contraction reach values at which even neutrons are destroyed, transforming into quark-gluon plasma, in which massive hadrons such as lambda, xi, and sigma hyperons begin to appear. This process is accompanied by a decrease in the energy of the core, and in this state it is capable of contracting even further. From about 2 × 10 to the power of 14 grams per cubic centimeter to about 3 × 10 to the power of 16 grams per cubic centimeter. Matter of this sort occupies a volume smaller than its so-called gravitational radius. A black hole is formed. Thus, in broad strokes, the further fate of main sequence stars looks as follows. The lightest of them will immediately turn into white dwarfs. More massive ones will end the same way, but only after passing through one or several phases of red giant evolution. And the most massive stars will end their lives as supernova, leaving behind either a neutron star or a black hole. Each of these types of objects, in turn, will undergo its own forms of evolution and transformation, most of which, however, remain purely hypothetical. Our universe is still too young for us to observe such processes directly. And in any case, the further transformations of stellar remnants lie beyond the scope of today's video, which has already turned out quite lengthy. So on this optimistic note, I will probably wrap things up. But if my viewers are interested, then in our future videos, we can continue this topic and talk about post-stellar evolution, the formation of black dwarfs, iron stars, black hole evaporation, and other fascinating, though largely hypothetical, processes. And if you enjoy what we do on our channel, you can support our work by becoming a sponsor here on YouTube or on our pages at Patreon and Boosty. A link to the latter, along with a corresponding QR code, should be appearing on your screens right now. And that is all for today. All the very best to you, dear friends, and see you again soon in our next videos.